Consider planar rigid body 1. It is rigid body means it will not deform whatever may be the forces acting on it. Or in other words, we can say if we will consider any 2 points on rigid body, distance between those 2 points will never change whatever may be the forces experienced by that body. Planar rigid body 1 is fixed. It means it will not move. On it, we are having another planar rigid body 2. Consider point A and B on planar rigid body 2. Planar body 2 is moving relative to planar body 1, and that motion will be in the plane of screen. As body 2 is moving relative to body 1, let us say at point A velocity is VA and at point B velocity is VB, which is shown on the screen. Line is drawn which is joining point A and B. Angle made by VA with line AB is theta, and angle made by VB with extended line AB is phi. If VA is resolved along AB, then component of VA along AB is VA cos theta, because cos theta is equal to adjacent side upon hypotenuse. Adjacent side will be component of VA along AB and hypotenuse will be VA. Therefore, component of VA along AB will be VA cos theta. Similarly, component of VB along AB will be VB cos of phi. The length AB is fixed because A and B are 2 points on planar rigid body 2. Hence, distance between A and B will never change. If VA cos theta, that is component of VA along AB, if VA cos theta is greater than VB cos phi, VB cos phi is component of VB along AB. If VA cos theta is greater than VB cos phi, then point A will move towards B and distance between A and B will reduce. But it is not possible because planar body 2 is rigid body. So another possibility is if VB cos phi, that is component of VB along AB, is greater than VA cos theta, that is component of VA along AB. If VB cos phi will be greater than VA cos theta, then distance between A and B will increase. But it is not possible because planar body 2 is rigid body. Hence, there is only one possibility. VA cos theta and VB cos phi should be equal or should be same. Then and then only distance between A and B will be maintained or it will remain same. As the length AB is fixed or it is not going to change in length, relative velocity between point A and B along AB will be 0. That is, VA cos theta should be equal to VB cos of phi. Now, line is drawn perpendicular to VA, hence angle between AB and line will be 90 minus theta. Now we will draw line perpendicular to VB, hence angle between this line and AB will be 90 minus phi. Recently drawn two lines will intersect each other at point P. Let us say PA is equal to R1 and PB is equal to R2. In triangle PAB, we can apply sine rule. In triangle PAB, angle opposite to side PA is 90 minus phi and angle opposite to side PB is 90 minus theta. So according to sine rule, we can write PA upon sine of 90 minus phi is equal to PB upon sine of 90 minus theta, which is equal to constant. So we can write PA upon cos of phi, because sine of 90 minus phi will be equal to cos of phi, and similarly sine of 90 minus theta will be equal to cos of theta. So we will get relation PA upon cos of phi is equal to PB upon cos of theta, which is equal to constant. So we will get relation R1 upon cos of phi is equal to R2 upon cos of theta, which is equal to constant, because PA is equal to R1 and PB is equal to R2. We can rearrange the terms and we will get relation as R1 upon R2 is equal to cos of phi upon cos of theta, which is equal to constant. And previously we have obtained relation VA cos theta is equal to VB cos of phi. If we will rearrange this relation, then we can write VA upon VB is equal to cos of phi upon cos of theta. Now we will equate and we can write the relation like this: R1 upon R2 is equal to cos of phi upon cos of theta. We can equate it to VA upon VB, because VA upon VB is equal to cos of phi upon cos of theta. That's why we will get relation R1 upon R2 is equal to cos of phi upon cos of theta, which will be equal to VA upon VB, which will be equal to constant. That's why we will have relation R1 upon R2 is equal to VA upon VB, which is equal to constant. If we will rearrange it, then we will have relation like this: VA upon R1 is equal to VB upon R2, which is equal to constant. So we have obtained relation VA upon R1 is equal to VB upon R2, which is equal to constant. It means velocity of point A and B are proportional to PA and PB respectively. VA is directly proportional to R1, that is VA is directly proportional to PA, and VA is also perpendicular to PA. One more thing, VB is directly proportional to R2, that is VB is directly proportional to PB, and VB is also perpendicular to PB. Now consider circular disc case, which is already discussed in previous video. Disc is rotating about center O in clockwise direction as shown in figure. So we can write VA upon OA is equal to VB upon OB, which is equal to omega, which is equal to constant. Omega is angular velocity of the disc. So how we can write relation like this? Because velocity at point A will be VA and it will be given by relation OA into omega, and velocity at point B will be given by relation OB into omega. So that's why we can write VA upon OA is equal to VB upon OB, which is equal to omega, which is equal to constant. So we are having relation VA upon OA is equal to VB upon OB, which is equal to constant. So we can say VA is directly proportional to OA. That is, velocity at point A is directly proportional to distance of A from center of rotation O of disc. Similarly, we can say VB is directly proportional to OB. It means velocity at point B is directly proportional to distance of B from center of rotation O of disc. And VA is perpendicular to OA and VB is perpendicular to OB. A and B are 2 points on disc and disc is rotating about center O. At point A we are having velocity VA and at point B we are having velocity VB. If we will draw perpendicular to VA and VB, those perpendiculars will intersect at O, which is the center about which disc is rotating. So by analogy with rotating circular disc, we can say at this instant or at this moment, planar rigid body 2 is having pure rotational motion about point P or about center P, because VA that is velocity at point A on planar rigid body, is directly proportional to distance of A from P, and VA is perpendicular to PA, or we can say VA is perpendicular to AP. Similarly, velocity at point B, VB, on planar rigid body is directly proportional to distance of B from P, and VB is perpendicular to PB, or we can say VB is perpendicular to BP. Means if we will draw perpendicular to VA and VB, it will intersect at P, which is center about which body 2 is having pure rotational motion. Planar body 2 is moving relative to planar body 1. Motion of planar body 2 relative to planar body 1 can be treated as pure rotational motion about point P or center P, but only for this instant or moment. So momentarily, motion of body 2 can be thought as pure rotational motion about point P or center P, and that center is known as Instantaneous Centre of Rotation. We are having relation VA upon R1 is equal to VB upon R2, which is equal to constant. Again, by analogy with rotating circular disk, we can say that constant is angular velocity of planar rigid body 2. So we will have relation VA upon R1 is equal to VB upon R2, which is equal to constant, which is equal to omega, that is angular velocity of planar rigid body 2, but it is instantaneous angular velocity of planar body 2. Instantaneous means it is only at this instant. Now consider point C on planar rigid body 2. Velocity at point C, Vc, at this instant will be given by relation Vc is equal to Pc into omega, and it will be perpendicular to Pc. Point P is Instantaneous Centre of Rotation, that is ICR, for relative motion between body 1 and 2. It is denoted by notation I12. I stands for ICR, that is Instantaneous Centre of Rotation, and 12 means it is ICR for relative motion between body 1 and 2, or we can even call it I21. But generally we will prefer notation I12, because in notation I12 numbers are in ascending order. Both notations are correct, I12 and I21, but we will prefer I12. Don't read it as I12 or I21, because it will not have any meaning. So we will prefer notation I12. Point P is ICR for relative motion between body 1 and 2. How point P or ICR I12 is obtained? Planar body 2 is moving relative to planar body 1. A and B are points on planar body 2. VA and VB is known, that is velocity at point A and velocity at point B is known. By drawing perpendicular to VA and VB, we will get point P at intersection of these perpendiculars, and that point P is nothing but ICR, or Instantaneous Centre of Rotation for relative motion between body 1 and 2, that is I12. At ICR, relative velocity between body 1 and 2 will be 0.